parts, statistics. This is all mathematics. You all love mathematics, I think, right? That's why you studied medicine. And okay, so in principle, statistics, don't be afraid of statistics. It is basically a tool to better understand what the data that you obtain or the data that you read mean. Okay? Statistics is a tool, it's not the final wisdom. If we say that relations are significantly different from this group to the next group, it does not mean that these people are from a different planet. The treatment is must-read, for example. Okay? So there's another term that I would like you to eradicate from your vocabulary. It's the term must. Okay? Statistics can only suggest. It is not a guarantee that something must work. If medication is significantly showing improvement of the well-being of people, that's not a guarantee. Okay? The only guarantee is that we will die. But we don't know if the treatments of the Achilles tendon problem that we talked about so much today, if you've got a treatment, okay, that this treatment, although it improves significantly in many studies, does not mean that this treatment will significantly also improve in you. Okay? It is suggested that it improves, but there's always there are always outliers. It is a way to better understand data and certain processes. But before we get started with all these statistics, we need to get familiar with basic statistical terms. And that's what we're doing now. N is a very, in any study that uses cohorts, for example, the term N is always in the text, and we're going to see that in this afternoon as well. N is usually nothing else than the number of individuals. Okay? The number of individuals or subjects in a study. For example, if you've got 76 participants in a study, then it's called N equals 76. That's all it is. It's very easy. It's very easy. Mean. The mean value is the average result of a test, survey, or experiment. The mean value. Now we have got here on the chart, we've got the height of people, 5 people. So this, the height of these 5 people range between 5 feet 6, 5 feet 7, 5'10", 5'8", 5'8", and the sum is 339 inches. So what we do is we basically divide the 39 inches by 5, which equals 67.8 inches, and that means simply the average, and the average is the mean, okay, is 5 feet 7.8 inches. That's very easy. So take the sum of all of that, divide it by 5, and that's the average. That's very easy. Now, what's a little bit less evident is the difference between mean and median. Okay, in all the studies that we are going, well, many studies that we are reading, we find mean, but we also can find median. Now, the median is a score that divides the results in half, the middle value. Okay, the middle value. Smallest, second smallest, medium, medium, and the tallest. Now, we must see that what we said, it is the half, okay? Here we've got 5 people, okay? 5, 6, 5, 7, 5, 10, 5, 8, 5, 8. Now, these 2 here are the median. It's not the mean. The mean would be different, okay? The median is the middle value. So what we do is we line up the number of, your numbers from smallest to largest and take the middle value. This is done when we have an odd number. So this is 5. If we had 6 people, that's a little bit different then, because we have no mean value. That we have no median value. So the even amount of numbers, we find the median of, for example, 7, 5, 46, 43, 16, 11, and 5. Line up all the numbers from 2 to 43. Add the 2 middle numbers, okay, and divide by 2. So the 2 middle numbers here, okay, 7 and 11, okay, we divide them and we see that the median number is 9. This is just for your understanding. It's for your understanding that mean does not equal median, okay, and we need to understand what that means. Mode is also a term, so we've got the 3 M's: mean, median, and mode. Mode is the most common result, most frequent value of a test, survey, or experiment. Example, find the mode of these here, put the numbers in order to make, these numbers that occur the most of the time. Okay, so these 5 numbers, okay, and we look at the numbers that occur the most of the time. That's called mode. Just explanations. It's not rocket science, but it's just nomenclature. Now it's getting a little bit more difficult when we look at terms like significance and p-values. We already said that what significant means and what p-values are referring to that. Now, significance. When we study, we try to see how different, again, not that they're different, but we try to understand how different results are, how different data are. And significance is a measure of whether the results of research were due to chance. The more statistical significance assigned to an observation, the less likely the observation occurred by chance. For example, if we were to line up all of us here, let's just line here, this wall here, and see, we divide then the smaller and the larger, or just we are very unbalanced here. We only have 3 women, right? So if we were to take the 3 women and the rest of the guys, and to see if the women are significantly taller or smaller than the man, okay? This is important. Now, the measure is it just by chance, or can we reproduce that? Okay, and this comes then. What is important is the example is a little bit false because we only have 3 women. So the number, the n, okay, the number of individuals is important because it would be unequally weighted. Only 3 women and whatever 15 men. Okay, that is not valid. The comparison would not be valid. But this is meant by significance. Again, the more statistical significance assigned to an observation, the less likely the observation occurred by chance. How can we determine significance? And we determine significance by mathematics, and we call it the p-value. The way in which significance is reported statistically is by the notion of the p-value. Now, what does a p-value mean? Here we have the p-value is smaller than 0.01. What does that mean? We see that in every good paper. Significant difference, and then we say p-value smaller than 0.01 or 0.05. Means that there is a less than 1% chance that the result of a study are due to random chance. So, what does that mean? That in less than 1%, the variation is true. Okay? We can now say less than 5%. Okay, so we can test it over and over and over again, and we assume that the result will be valid in 95% of all observations. But 5% we accept an error. So 5% of these studies we expect that there can be different. But that's okay. We can say 3%, we can say 1%, we can say 7%. There's nobody who carved that in stone. There was Mr. Fisher, who was not related to Mrs. Fisher, but he lived 100 years ago, who was the Pope of statistics, and he came up with the idea that 5% is acceptable, and we call anything that is larger than 5% of variation statistically significant. So, and I give you an example now. A study had one group of students, A. Okay, let's say this is one group of students here. Study notes they took during the class. Okay, so you take all notes that you study during class. The other group, B, let's imagine this is the same amount of people. Okay, you took notes after class using a recording. So you didn't attend the class, you just listened to a recording. You didn't see me, just listened to the recording. Students in group A scored higher on a test than group B. The study reports a significance of p smaller than 0.01 for the results. What does it mean? This means that whatever the reason, students who took notes in class did better on the test. There is only a 0 to 1% chance that the results are due to some random factor. Okay? So we expect that taking notes is better than listening to the recording of this class. That's what we did. Okay? Notes immediately taking after class, and notes of recording of class. And same group, same, not the same group, but the same amount of people, and we can see that this is faring better. Hold on. Is significance and the p-value clear? Also for those people that did not have any statistical background yet. Okay. Now we have correlations. We already talked about these. The degree to which two factors appear to be related. Okay, correlation should not be confused with causation. It's very important. Just because two factors are reported as being correlated, you cannot say that one factor causes the other. For example, you might find a correlation between going to the library at least 40 times per semester and getting high scores on tests. However, you cannot say from these findings what about going to the library, or what about people who go to libraries often is responsible for higher scores. Correlations, that's what we said this morning, does not mean causation. Okay, there's correlative evidence, but not causative evidence. If we were to take for example, one example, running now during coffee break. Okay, 5 colleagues here. You run to the bridge and back. We measure the blood pressure before and after, the heartbeat before and afterwards. Okay, and your heartbeat goes up by, let's say, 30 beats. And you do the same. Okay. What may be the difference? Can we use a correlation, or what kind of test would we need to do? So we all running, okay? Running to the bridge and back, running to the bridge and back. 5 people and 15. No, just a group. Group 1, group 2. No, the question is again, how different are people from group A to group B? Are they significantly different in gaining heartbeats, for example? Would a correlation be the correct method? No. Okay, this is something that we would do with a t-test. Okay, we call it a student's t-test, and most of you have heard about the student's t-test. Okay, this is not a correlation test. A t-test only wants to understand if there is a significant difference between group A and group B. If we were to divide group A, group B, and let's divide it to group C. So we've got 5, 5, and 5. Okay, we've got 3 groups. We would not be able to use a t-test anymore, but we would need to do an ANCOVA. Or we would need to do 3 t-tests, because a t-test can only compare one group with another group. But because we've got 3 groups, okay, we need to do comparisons between 1, 2, 2, 3, and 3 and 1. Then you get 3 values. Okay, or you do an ANCOVA, which is an ANOVA, which is an analysis of variance, where you take all the groups A, B, and C in one column, and in the second column you assign group A to 1, 2, and 3, and then you compare these groups. It's a different method. This is statistically a little bit more solid, okay? We can't do that because we don't have time today to do all these statistics, but this is very important that we talk about these. Correlations is something different. Correlations can be done if you've got a variable that is continuous from 0 to infinity. Okay? And you expect also a continuous response from 0 to infinity. This is what you must expect. Okay? You don't have a restricted finish. And it must be normally distributed. The data must be normally distributed. If you do not have a normal distribution in your data, you must transform the data, and the data transformation is often log transformation. So you make it in Excel. You can do that quite easily. You log transform the data to meet the assumptions of normal distribution. You know all of that? Most of you? Okay. Now the R value. The way in which correlations is reported statistically is the number. Basically, it goes from 0 to 1 or from 0 to minus 1. The R value of minus 1 indicates an extreme negative correlation between two variables, as one variables tend to increase, the other variables tend to decrease. For example, if we have got here a number of observations, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, n equals 11. Okay, these are 11 observations, and we must know that we have no finish here. Okay, this is a continuous variable here, the predictive variable, and we must allow that all of these variables are weighted equally. So all of them have the same chance to score here. Okay, and the strength of the R value depends on how closely these individuals are plotted next to this correlation line. Now this can be a very steep line, it can be a very flat line, it can be on the other side, so it can be a negative line. It can also be a hump-shaped line. Okay, this would be a logistic regression. The R square just tells you how closely the data are around a correlation line. Is this clear? Is there anything that is completely missing?
When we are measuring the ICC between two different operators that are doing a procedure, we are using the statistic R value. It is correct?
Well, that's a good question. If you do if you use the R value, you must always use also the P value. An R value tells you, for example, we don't have a blackboard here right now.
I try to clarify my question. When we are speaking about inter-observer correlation coefficient, we can express it by means of R value?
Yes, that's right. Okay, that's right. But this correlation coefficient is must be substantiated by the P value, because you can have a high R square, but the P value is high,
okay.
Which means you can only say there is a statistically significant correlation, okay, if we find the P value smaller than 0.05 or whatever you normally in statistics it's 0.05.
Okay.
Okay, so you can also have an R square value, and
multivariate statistics, that's quite often the case, which the R-square value is pretty low. It could be R-square of 0.2, 0.3, okay? But it's significantly, statistically significant. So that would mean, again, that there is only a 0 to 1% chance that the results are due to some random factor. So you can explain an R-square value of 0.3. What does it say? It says that the variation observed, okay, the predictive value explains 30% of the variation of the response. 30% of the variation in the response can be predicted by the X values of the predictive variables. Statistically significant. If the p-value is smaller, as we said here, there's only, if the p-value is 0.05, we would say only 0 to 5% chance that results are due to some random factor. So R values are important, but only meaningful if you get also the p-value attached to it. And the p-value is important if we assume that statistically significant values are put at 1% or 5% or 3%. Typically it's 5% chance that results are due to any random factors. Okay? So you can repeat and repeat and repeat and repeat these results, and it should be always significantly different. Okay, correlations again. The correlation values here are important if you want to see how a treatment affects something, right? So you don't want to understand how different the groups are, okay? You see, I always say the faster you drive, the more fuel you use, okay? The slower you drive, the less fuel you use. You can try and do that. You can do it even at home and take notes and make these nice plots, and then you run the statistics and you see that this is high R-square value, and probably it's also significantly different. And so these are just correlative statistics. If we want to compare systems or groups, we use a t-test. And these t-tests can be done in Excel. These are very, very simple t-tests. Or you use statistical programs if you want to do that yourself. The cheapest is what we call R, just R, like the letter R. It's for free, but you need to learn. So the learning curve is a bit high. It's for free, so we all use R because my students have no money, and they all need to learn R. It's for free. You can download it, and that's what we do. If you want to simply punch in data and say the basic statistics that you would like to do, you can use methods and programs like SPSS. What I can do is, hold on. This is, first of all, a book, Practical Statistics for Medical Research. I printed down the website where you can find this book. You can also find this here. This is a North America website where you can find basics on statistics. And what I do now is I close that for a second, and I'll show you on the internet. We don't have internet here? Oh yes, here it is. But no, yeah, here it is. It doesn't work now? Okay, for some reason it doesn't show here on the screen. Oh, I see, okay. Then I have to, okay, sorry, then we have to go back. I'll write it down here for you. So this is called SPSS. This is one of the best programs. Then there's also one that is called Statistica. I'll put that back large on the screen. Yeah, so this is what's it normally, it's SPSS or Statistica. These are programs that are quite helpful if you do basic statistics. And there's other programs as well. It all depends of the methods you'd like to do. In general, if you're not very solid in statistics, and many normally are not, because that's not your profession. And if you want to do a study, I would highly recommend that you consult a statistician in the beginning of the study, not only when you get the data. Every statistical project needs to be planned with a statistician. Okay, this is extremely important, because the worst thing that can happen to you is you come up with a study, you've got data, but you can't use them because the people are not randomly distributed. That's right. The data are not normally distributed. They are wrong. You have missed something. You have got you violated some statistical assumptions. All of these things need to be taken into account before you do an analysis. You also do the same thing if you do only, under quotation marks, a literature review. if you were to do a meta-analysis of data, please always consult somebody who knows about statistics. That's really, really important. Because otherwise you risk lots of work and lots of time, maybe even money, and you don't want to get into problems afterwards. Are there any questions so far? It's all good? Then I'll suggest that we break for coffee and come back. How long is the coffee time? 15 minutes? Okay, so 11:15 then.